thanks for coming to listen to my talk, and thanks to Hemi for hosting us, and thanks to Peter and Stefan who couldn't be here for organizing. I'm going to talk about internally four-connected binary matroids. I'm going to discuss the splitter theorem for them. This is based on some joint work with Dylan Mayhew and James Oxley, whom you'll find in the audience. And they are at Victoria University, Wellington, New Zealand, and Louisiana State University in the United States, respectively. And I'm currently at Brunel University as a postdoc, but in 2016, I'll start a permanent position in the United States Naval Academy in the United States. Nous sommes les moutons. So in order to talk about internally four-connected binary matroids, I'll tell you what what internally four-connected means, and we'll build up to it. So in order to talk about connected matroids, I'm going to talk about some disconnected matroids. If you have a graph that breaks apart as a direct sum, like this is a direct sum. You have a vertex in the blue graph and a vertex in the red graph, and you stick them together to get your graph on the right. So the graph on the right is a direct sum, and that's a sign that your graph is not two connected. And when your matroid breaks apart in that way, if you have two separate components that don't overlap at all, then you have a disconnected matroid. And in the matroid, it will be the set of blue edges and the set of red edges that give you your separation. If you have a graph that breaks apart as a two-sum, then you have, this means that you have a green edge and can you see the green edge? Yep. A green edge in your blue graph and a green edge in your red graph, and identify them over that edge. And then you remove that edge. And so this graph over here is a two-sum of these two graphs. And that two-sum is a certificate that your graph is not three-connected. And if your matroid can break apart in a similar way, then it's going to fail to be three-connected. And this talk is going to seem very graphy, so I'm going to use a lot of, I'm going to show you graph pictures inside binary matroids. So you'll see a lot of vertices and edges, so you should get used to it. If you find it uncomfortable, then just suck it up for an hour. So this is not considered a two-sum. Basically, every graph breaks apart as a two-sum if you consider, well, I can just take a pair of parallel edges, identify one of them as my green edge, and then stick that onto my red graph, and what I get is going to fail to be three-connected, and that would just be silly. So we would put some restriction on each of the graphs. We'll say you have to have at least 3 edges in each graph in order for it to count as a two-sum. So this is not a two-sum. And there's chain theorems that deal with two-connected matroids. And if you have, a chain theorem tells you that you have an element that you can remove in the right way, keeping your connectivity. So Tet showed that if you have a two-connected matroid, then any element that you take, either you can contract it or you can delete it and stay two-connected. So any element can be removed in the right way to stay two-connected. So that's a really important inductive tool. And you can also apply that to graphic matroids, obviously. He also showed that if you have a three-connected matroid, then there exists some element that you can remove in the right way to get a three-connected minor. So the way I've written this is maybe a little bit strange looking, but it's a format that you'll see come up again, so I put it in this way. I've said that if you have a three-connected matroid, then it has a three-connected minor that's one element different from the original guy. There's one exception in the graph case and 2 exceptions if you consider binary matroids, well, if you consider all matroids. The exception in the case of graphs is a wheel. If you have a wheel, it's three-connected. It doesn't break apart as a two-sum, but each of your edges in your graph is in a triangle. So as soon as you contract one of those edges, you're going to create a two-sum. So there's no one element contraction that you can do. And as soon as you delete any of these edges, because they all are incident with a vertex of degree 3, you'll create what's called a series pair, and that's also an indication of a two-sum. So there's no one element move you can do to get a 3-connected minor in the case of a wheel. And if you take the outer cycle and you relax it, you get a whirl, and that also has no one element move. And those are the only exceptions. So higher connectivity, we'll continue along our pattern. We're going to say our graph is internally 4 connected, so that's the number after 2 and 3. You go 1, 2, 3, internally 4 connected. An internally 4 connected graph or matroid is where it doesn't break up as a 3-sum. Here I've got a triangle that's green and another triangle, and when you glue them together across the triangle and remove the triangle, what you get is not internally 4 connected, because we've got a 3-sum. Just like in the case of the 2-sum, there are some things that might look like a 3-sum, but they don't actually count for our purposes. Like if you took a doubled triangle and you glue it onto something, you would get just that original graph back. So you could say, well, if that counts as a 3-sum, then anything that has a triangle in it fails to be internally 4 connected. And we're going to say, no, that doesn't count. Since we're matroid theorists, we'll also say that the dual of a triangle, which is a triad, doesn't count as a 3-sum. You have to have at least 7 edges on each side, or 7 elements in the case of a matroid, for it to count as a 3-sum. So this is still internally 4 connected, and as soon as you add your 7th edge to the left-hand side, you do get a 3-sum. And what the 7-edge set looks like in the resulting graph is called a 4-fan. And you can see here there's a triangle, and one of its vertices has degree 3. So in the binary matroid, you have a triangle meeting a triad. So this is our internally 4 connected bilater. And it's just really bad. It's bad news. This is the thing that we want to avoid, and it haunts our bad dreams, our nightmares. So we showed in 2011 that you can get a chain theorem for internally 4 connected binary matroids. So this has a corollary for graphs. And the bound is not as nice as the bound for 3 connected. As you would expect, it gets a little bit messy. You have, if you have an internally 4 connected binary matroid, then it's got an internally 4 connected minor that's at most 3 elements away. So maybe you do 2 contractions, or you do a deletion and 2 contractions, or something, and that's all you need to do in order to get an internally 4 connected minor. Or you have to list the caveats now. You may have a situation like one of these 3 graphs, in which case you're going to need to do 4-element move. So here's a graph called the Terrahawk, where you can remove this vertex. If you just remove those 4 edges, what you get back is a cube. That will be internally 4 connected. But if you just were to delete one of those, you would expose a 4-fan. Actually, worse, you would expose a 5-fan. And this is a quartic planar ladder. And as soon as you delete one of those edges, you expose a degree 3 vertex that's touching a triangle, which is a 4-fan, bad thing. But what you can do is contract 2 edges in the circles, and then you'll get 3 edges that are parallel and delete 2 of those, and that's your 4-element move. And this is a quartic Mobius ladder, so it's a ladder that has a half twist on it, and you can do a compression move on that too. So Seymour, now I'm going to talk about some splitter theorems. Seymour showed, and Brolaski showed, they proved it independently, that if you have 2 connected matroids where one is a minor of the other, then you can take an element that's in M, that's not in N, and you can remove it in the right way to keep the minor, and to keep to connectivity. So if you had a two connected minor here that didn't contain E, then, well, deleting E is going to leave this pendant edge, which is bad. That's not going to be two connected. But nothing will go wrong when you contract E to your minor. It turns out if you have a two connected minor, it can't use that pendant edge, and it all works out. For three connectivity, Seymour has his splitter theorem, which says that if you have two three-connected matroids, and you have n is a proper minor of n, and you have to have a bound on the size, n has to have at least 4 elements. And if n is a wheel or whirl, then m has no larger wheel or whirl minor. Then there exists some intermediate matroid, m prime. M prime is always going to be my intermediate matroid, where m prime has an n minor, and it's one element away from m. So this is giving a bound of 1, and it has to do with being careful with what things you allow n to be, and what your wheel and whirl minors look like in your matroid. So what do we know for internally 4 connected matroids? Well, Johnson and Thomas talked about the graph case, and there's been some controversy as to what exactly was shown in that paper, and did they prove a splitter theorem where you keep internal 4 connectivity in your intermediate graph, or didn't they? So I'm going to answer questions about this paper in this talk. So I'll show you what Johnson and Thomas did. Gillen and Joe in 2006, and Joe with another paper in 2012 talked about the internally 4 connected case for binary matroids, but they found an intermediate matroid that had a weaker form of connectivity. So they didn't find an intermediate matroid that kept a minor and kept internal 4 connectivity. So that's what we're looking for. So what did Johnson and Thomas show exactly?
Sorry, Carol, what was the weaker form of connectivity?
So in internal 4 connectivity, you don't have any of those 4th fans, but I mean, there's worse violators of internal 4 connectivity than 4 fans. You could imagine a triad that needs 2 triangles, so it would look like a 5 fan. They used 4-4S connectivity, or 4-4 connectivity, where you allow your violators to be 4 fans and quads. So if you can break it apart as a threesome, you have at most 7 elements on one of the sides. You have a smaller side, but there's at most 7 elements. So they do avoid like 5 fans. And it's called 4-4 connectivity, and it's much more manageable.
Wait a minute.
I mean, 5 fans only got 5 elements.
Wait a minute. I mean, quads don't arise in graphs.
Yeah, but they were talking about binary matroids. They were talking about...
That's the
I'm
game.
sorry, were you asking about the result for binary matroids?
Oh, sorry, I got confused.
Yeah.
But I just something I was a bit confused about. You said something about they allow 7 element tree separators.
So,
So
I was
5
thinking
fans.
about doing a threesome where you have the 3 elements that you're going to delete in the...
Oh, you're
That's
so,
So
3 elements
when you
plus
break it
4.
apart as a threesome...
oh, so you're not just counting the number of elements in the
No,
separator, you're
I was also
adding
thinking-
something to that.
3 plus the
Yeah.
4.
So it's you have 4 elements on each side that persist in the
Yeah.
matroid, but yeah. So splitter theorem, we're going to talk about a splitter theorem for internally 4 connected graphs, and this is from the paper Generating Internally 4 Connected Graphs by Johnson and Thomas. First, they the same way that Seymour said, well, if n is going to be a wheel or whirl, then m has no bigger wheel or whirl minor. and I put the splitter theorem up in that form because Johnson and Thomas do a similar thing. They say, well, if you're going to have n being one of these graphs, so this is a cubic planar ladder, or rank k or whatever, a cubic Mobius ladder, and I've got a cubic planar biwheel, that's what they call it, and a cubic Mobius biwheel, which is different just by that kind of axle between the two hubs. Then you have to be careful that M doesn't have a bigger minor, well sorry, G, because we're talking about graphs, that G doesn't have a bigger minor that falls into one of these categories. So if N is a cubic planar ladder, then you don't have a quartic planar ladder of the same rank as a minor in your graph. That's one of the things that they stipulate. And if you have a cubic Mobius ladder, then you don't have a rank 1 higher quartic Mobius ladder. And if you don't have, if N is your cubic planar biwheel, then you don't have the quartic planar biwheel, and the same for the Mobius biwheel. Because these are graphs that will give you problems. You can see that sort of removing any edge from here is going to, well, if you delete it, it's going to expose a 5-fan. As I was talking about before, you'll have a triad that's meeting 2 triangles. If you contract it, you get some parallel elements. It's going to be potentially problematic. And you can imagine picking your N minor that you want to preserve in a way that just makes it as horrible as possible. So they make that stipulation. So they had 2 theorems in this paper that are splitter theorems. They say if you have 2 internally four-connected graphs, where H is a minor of G, and if H is a cubic planar ladder, cubic Mobius ladder, or whatever, then G has no thing that you want, none of those things that you want to avoid. And then you're able to say something about an intermediate graph. And here's where it gets maybe controversial. Something that might happen is your intermediate graph is an uncontraction of your minor that you're trying to keep. And when I say you're keeping a minor, you're keeping a copy of a minor. You may not keep the exact same edges that you have in H. You may be getting an isomorphic copy. So it may be that H prime, your intermediate graph, is an uncontraction, but there's nothing in their paper that tells you this has some bound on its connectivity. You may have lost internal four connectivity when you did this uncontraction. You don't know anything about it, except that the nice thing about it is that it's just a one-element move. So you do a one-element move to get an intermediate graph. We don't know about its connectivity. This is the move where you keep internal four connectivity. It's called an addition extension. So they defined an addition extension. Well, you take H and it sits in your graph G, and you think about adding edges into H from G so that you build something step by step where you have a handle on the connectivity. So I'm going to add an edge to H, and now I'm going to create at most one four-fan. I'll create one four-fan, and that's my worst thing. And now I'm going to add another edge to this graph. Now I don't have that four-fan that was that I created. I create at most one new four-fan, and I keep continuing with this adding of edges. So these are single element extensions until I add the teeth edge, and that brings me back to internal four connectivity. So this is an unbounded move. There's no bound on what T will be, but at the end, you still have the same rank as H, and you've got an internally four connected graph, has an H minor, is a minor of G. So that's your one result where you get internal four connectivity. And the third option from this theorem is that you do a special extension in your minor H, and that, again, there's no guarantee about the connectivity that you're going to get. Although, just from looking at these extensions, they look internally four connected to me. And these are the extensions that they're talking about. They talk about a quadrangular extension, and a pentagonal extension, and a hexagonal extension. So I've drawn them all on the same page. For the quadrangular extension, you have a 4-cycle, and here I've circled vertices to indicate there's no other edges that are incident with those vertices. So this is a degree 3 vertex in the graph. So this is sitting in your graph somewhere. That's not the whole graph. Obviously, that would not be internally connected if it looked like that. So this is sitting in your graph, and that will be your place where you can do a quadrangular extension. If you have something that sits like this in your graph, that's a place where you can do a pentagonal extension. And you have 2 degree 3 vertices in a 5-cycle, and you don't have either of these 2 edges. So those 2 vertices are non-adjacent, and those 2 vertices are non-adjacent in your graph. That's has to be that way. And if you have a 6-cycle that looks like this, then that's an opportunity to do a hexagonal extension. So you have a 6-cycle that contains 3 degree 3 vertices, and there's no vertex in your graph that's that's adjacent with those 3 vertices.
And adjacent with those only, or
And adjacent with those only, yes. So there's no degree 3 vertex that's got those 3 vertices as a neighborhood. And then your extensions look like this. So here, these vertices are still circled because now they're degree 4 vertices, but those are all the edges that are incident with them. And this is, here I've added 4 edges. In this case, what I do is I delete one of my edges from my cycle. Basically, I took that edge, I added 2 edges to make a triangle with that top vertex, and then I did delta y. If you like thinking about delta y's, that's what's going on there. If you want to think about it another way, you just delete this edge and add this degree 3 vertex that's incident with those. But you can see that the original graph is a minor of this. You could just contract this edge and delete that. And this is the hexagonal extension.
Why did you insist that there was that degree 3 vertex didn't exist in the hexagonal case? I can't see any violation of internal 4 connectivity.
What if you take those 6 edges? So take the 3 dashed red edges and the 3 blue edges.
Yeah.
That would be a violator of internal 4 connectivity.
It's not a fourth hand, but
So
What do you get was of degree 3?
That's a stipulation of the construction. You'd have to ask Thompson. But these are nice moves because, I mean, maybe they're pretty, you think they're pretty, but they're bounded. So you have a 4-element guy, a 3-element guy, and a 3-element guy. So I built up from H to H prime, and it's a minor of G, and it's kind of a bounded way away from H. So my 3 moves, one of them was an uncontraction to who knows what connectivity. One of them was a series of extensions, just throwing in edges, to get an internally 4 connected thing. And one of them is just doing one of these really highly constructed or highly structured additions.
But you said that they didn't prove that these moves produce internal 4
Yeah, it doesn't say anything there that it's internally 4 connected, but it doesn't seem like they can violate internal 4 connectivity from these structures. So maybe I just needed to read the proof more carefully or something, but I was just looking at the results. So this is the theorem that I just discussed, the splitter theorem. But they had another theorem in this paper where if you add some more conditions, then you can get an even nicer result. So again, for their theorem 2, you have to be careful about H and your minors of G. And H is not going to be K33, and it's not going to be the cube, and G is not going to be, is not allowed to be one of these graphs. And it may sound strange, but you take all the degree 3 vertices in your graph H, and now look at the graph that H induces on those vertices. And this graph has to have trees or cycles as its components. I know it sounds kind of strange, and I'll show you in a second what happens if you take away that condition. But as long as all that holds, so this is slightly more restrictive than theorem 1, then you can find an intermediate graph that's going to be an uncontraction, or it's going to be a single element addition extension, and it's going to, this graph is going to be internally four-connected, or you get one of these extensions, the pentagonal extension, the quadrangular extension, or the hexagonal extension. So the nice thing that we have here is that t is equal to 1, essentially. So I haven't written on the slide that h prime in this case is internally four-connected, but it is.
So in the case where you decontract an edge,
Yeah.
you don't have a guarantee of internal four
You
connectivity?
don't know, you know what the connectivity is. Yeah. So I was interested in the cubic. I mean, why do we want to look at the vertices of degree 3? Well, if you take, here's a problematic case. Suppose that this is your minor, and suppose your major is just, well, turn this bit of cubic ladder into quartic ladder, so throw in some diagonal edges there. That's not, you're not going to be able to put a bound on the sides of the move that you would be able to do. But this is not allowed to be H in that last theorem, because if you look at the degree 3 vertices, those are the blue ones, and you induce your graph on those vertices, you get a component that's not a tree and not a cycle. It's this graph. So they would not have allowed this as your minor in that last thing. So actually, it's imposing some nicer structure. So now we want to talk about internally four-connected binary matroids, and we have to deal with all the same problems that they dealt with, but we don't want to find, we don't want to settle for less internal four-connectivity. So in the case of a double wheel, what can we do to get an internally four-connected minor? Does anybody, since this is an interactive workshop, can anybody have a bounded move that you can do that doesn't produce any four fans? No, that's a lot to ask at this hour.
Contract an edge in the ring and lead to
Yes. 10 points for Rene Pavotos. If you contract one of these edges along the rim of your double wheel, then you'll create two parallel pairs, and then delete one edge from each of those pairs. So that's a 3-element move. What you've got now is a smaller quartic double wheel, which is internally four-connected. So that's one move. Another move, well, we're doing a splitter theorem here, so it may be the case that N, our minor that we're preserving, has full rank, has the same rank as our original matroid. In that case, well, we can start deleting things. As soon as we delete one of the rim edges, you're not going to be able to recover. Yes, James is correct. This is what happens. You basically shot yourself in the foot. As soon as you remove one of these edges, you can see that that's actually just a double fan then, and it's you're never going to recover internal four connectivity. You're in trouble. So the only thing that you can do is trying to delete one of these spokes. As soon as you delete a spoke, you've exposed a degree 3 vertex that's incident with two triangles. So it's a 5-fan. Well, to get rid of that 5-fan, since I can't contract anything, I better start deleting things. And you find yourself deleting edges all the way around, both the top and the bottom, to get down to a cubic bi-wheel. And what about this guy? We have to deal with him. He's a problematic structure.
I think her would be a bit of no.
We'll call this James. So suppose James, if James is your matroid, because graph graphs are binary matroid, then he's going to give you problems. You know that. I already talked about a compression move. You could imagine contracting 2 edges on your circles, and then you get a parallel class with 3 edges, and then you can delete 2 of those, and what you end up with is a smaller quartic planar ladder that's internally 4 connected. But what if your minor has full rank again? What are you going to do? As soon as I start deleting things, suppose I delete this diagonal edge, then I expose a degree 3 vertex here and a degree 3 vertex here, and those both meet triangles. So if I start deleting things, I'm going to have to delete all the way around the ladder. That's another unbounded move. And you have the same problem with the Mobius ladder, except that with the Mobius ladder, if you're not going to do a compression move, and you start deleting all of your diagonal edges, you'll find that you end up with a degree 2 vertex. And then you have to do a contraction. I have a diagram to show that later on. But that's another unbounded move that we'll have to deal with. And you can imagine, well, this is a problem, but it's a really nice looking binary matroid. We'll just throw into the class of exceptional cases, and who cares anymore. But you can imagine opening it up, like take these 2 vertices, pull them apart, and stick another graph in there, a binary matroid. If you glue this onto a binary matroid in some way, you have the same problem. You don't eliminate this problem by saying, well, we just have to deal with this case. This thing could arise in your matroid in an unexpected way. And here's the Terahawk, and we'll have to deal with that again. We said that you can contract that. I mean, you can delete all those edges in the middle. Or you can contract the outer 4 cycle. What do you get if you contract the outer 4 cycle? You get a Bible, or the octahedron, whatever you want to call it. So here's the theorem. We have 2 internally 4 connected binary matroids, where n is a minor of m. Then we're going to find an intermediate internally 4 connected matroid. Where we have to do at most 3 moves. Up to here, I'm saying up to duality. And I'll give you graph pictures, and I'll say up to the duality, this is what's happening, and it may be confusing to try to think of, well, what's the dual of that move in, if we're looking at the dual of that, and all I have is a graph picture of the one. But you can use your imagination or ask me about it after the talk. So, in the case that you have the 3-element move or most, we call that a quick win. You may have a 4-element move that you can do. We've already seen one of those moves. It looks like deleting a 4 co-circuit. This is called a good augmented 4-wheel. It's a good augmented 4-wheel because deleting that green edge it only exposes 4 fans. That's the worst problem that you have in the graph, and you remove that.
What do your arrows mean?
Arrows are contractions.
Yes, okay.
So here I'm suggesting to contract 2 edges and delete the dashed edges, and that's a compression move inside a bit of quartic ladder. So these are 2 4-element moves.
What does it mean to have degree 3? Like, what do the red circles mean measurably?
Oh, that's a good point. So these graphs are sitting inside my binary matroid structure, and I've drawn this graph, but I'm not trying to insinuate that the entire matroid is graphic. I'm trying to use these diagrams to keep track of the cycles and the co-circuits that I know about. The circuits, use the right word. So what I know about my binary matroid is that I've got 5 triangles that are in this pattern, and I've got 4 co-circuits, I've got 4 co-circuits and I have 4 of them. And they're in this pattern.
Wait, hold on.
Hang on.
How many co-circuits do you have?
I got lots, like a lot.
Okay.
So you have a lot of them, a lot of these co-circuits, and I've circled them to indicate they are genuine co-circuits. So I'm not trying to insinuate that there's a 2 co-circuit over here. I'm just talking about, or I'm just insinuating that I genuinely have co-circuits there. And the same for that diagram and all the diagrams that I'm going to use. So these are 4-element moves that will get you back to internal 4 connectivity. 4 elements, still not so bad. Here's an unbounded move that you may have to do. So sitting inside your double wheel is a double fan, and you may have to do alternating deletions to get down to your minor. You may have a set of triangles. We call this a bow tie ring because the triangles meet in these 4 co-circuits, and when you circle them, they kind of look like bow ties. So if you have a structure like this, then you may have to delete an edge from each one of the triangles, and depending on the length of your bow tie ring, it might not be just 4 edges, it could be 100 edges. You can't put a bound on it. In the graph case, if this actually is if we're starting with an internally 4 connected graph, then this actually does become a cycle. These bottom edges form a cycle because these vertices have to be the same. But in the binary case, it's not true. So this is trimming a double fan. This is the bow tie ring, and you trim it by removing an edge from each triangle. And you trim a ladder with quotes around it. So if you have one of these structures in M, then preserving your N minor and internal 4 connectivity can be accomplished in some cases by removing the dashed edges. And here, your structure is more highly constrained than I've shown. There's more co-circuits. You have either a 4 co-circuit here, that's a 4 co-circuit, or you have a 5 co-circuit that includes this edge, this edge, this edge, this edge, and this edge. So it's tricky. If you're starting off with a graph, then you have to have the 4 co-circuit. You can't have the 5 co-circuit case. It's not graphic. But in the binary Matroid case, you don't know. And the same is going on with this vertex. Either this is a co-circuit or this set forms a co-circuit. And those are laddery structures because they're not actual ladders. I can't take the quotes off of that word ladder because I may have 5 co-circuits in there. So 3 is the enhanced ladder move or lobster move. So again, we're coming down from M. Johnson and Thomas, they built up from H. We're going the opposite direction. You may have a structure like this, which is, it's really fun to try to look for it in a binary Matroid because you have to build it kind of like piece by piece, and it's a bit excruciating. But in the end, if you extend it as far as you can, and when you reach the end of being able to extend it, you either find a quick win or one of the other wins that we've described, or this is your win. This is your enhanced ladder move. And we call it an enhanced ladder because you can kind of uncurl it in a way to make it look more laddery. But it's just the deletion of all those dashed edges. It's another unbounded move, but it's highly structured. We've got all these circuits and co-circuits. So you really know what you're looking for in M to do the deletion from. This is another enhanced ladder move. You can imagine having to cap off with a curl right there. And here's what I'm going to show you how to if you sort of unfold the yellow triangle and the purple triangle, then you get something that looks more laddery when you display it like this. You're kind of missing 2 edges, but That's why we call them enhanced ladder moves. And they're graphic structures. It really is graphic structures that give you problems in the binary Matroid case. So maybe that deleting all of those edges, all these dashed edges, is the only thing that you can do. And in that case, that's going to give you an internally fork-connected Matroid.
So if you unfold the yellow and the purple triangles, that's just a different structure, right?
This is the same. This is this. This
Whoa,
is
hold
this.
on.
This.
What? Wait.
So what I do is I ignore this 5-co circuit. Just forget about that 5-co circuit.
Yeah.
Vertices don't actually exist. They're a
Sure.
figment of your imagination. I've just drawn those edges incident with that vertex so that I can put a circle around it and say that's a co-circuit.
Yes.
But forget about that 5-co circuit. And I'm going to I'm going to grab this and pull it
Yes,
over to
okay.
here. And I flip the edges up. Can you see it one more time?
But you're not. But the thing is, you're not displaying that 5-co circuit.
I'm not displaying that 5-co circuit. Yeah.
Right.
It's still there, but I didn't want to draw it in and confuse the issue. One more time?
You certainly wouldn't want to confuse the issue. That's true.
This is a lobster move, and it's called a lobster move for historical purposes. I asked Nomenclature Man what we should call this move, and he had to think about it. So I was using lobster move in our papers as a placeholder, because I knew the word lobster would not appear anywhere else in the paper, and we'd be able to do an easy search and replace. But then we got attached to the name, so now we still call it a lobster move. And it kind of has like antenna on it. And this is the structure that may sit inside your binary Matroid, and all the other structures that I've shown you, the elements are all distinct. But in this case, it may be that the blue edges are the same and the rest of the elements are distinct. Or it might be the case that this triangle is the same as this triangle and the rest of the elements are distinct. So this may be obscuring some more structure. It may actually be some kind of ring or something. But this is a case where I do a bunch of deletions and then a contraction at the end. And what I get is going to be internally fork-connected. So that's the lobster move. So those are 3 more unbounded moves, but they're highly, highly structured. I'm going to look up and see what's there. So we've got these 3 parts of the theorem so far, but we're not done yet. That's why we have the ellipsis down here. It could be the case that you genuinely have M being a quartic Mobius ladder and N being a cubic Mobius ladder. In the case that we had a quartic planar ladder, let me show you in the previous slide. If I had a quartic planar ladder, then there would be this structure sitting inside there. You can imagine this bottom set of edges just being the inside cycle of your quartic planar ladder, and then the deletion from each of these triangles will give you a cubic planar ladder, which is internally fork-connected. So this deals with the quartic planar ladder case, but we haven't dealt with the quartic Mobius ladder case. That genuinely is an exception to any of the things we've talked about so far. And as I said before, you can do your deletions around the edge, around the cycle, but when you get to the end, you're going to leave a degree 2 vertex. I promised I wouldn't use this, but I'm going to use it right there. So we have a degree 2 vertex when you do all the deletions, so you need to do contraction to get your, it's got rank 1 less, but it's your cubic Mobius ladder. So quartic Mobius ladders have to have an odd number of vertices, cubic Mobius ladders have to have an even number of vertices, so you have to lose rank.
So you've got the arrow on the wrong edge then, haven't you?
Yeah, I have that arrow on the wrong edge. Sorry about that. That is an optical illusion. It should be right there. I should have worked harder on these images. This is another one of our exceptions. And here I've left the realm of graphs and drawn a graft, or a hypergraph. This is a wheel. Dylan, can you stop obscuring my slides, please?
Sorry.
This is a wheel with an odd number of spokes. And there's another element, my binary matroid, that is drawn here as a hyperedge incident with every vertex. So this looks like a degree 3 vertex, but it's not. There's actually a 4 co-circuit. It's each of these 3 edges and my hyperedge. So the hyperedge is there interacting. If you think about the incidence matrix of your graph, then adding a hyperedge is just adding another column to your binary matroid. So this is another problem. And this is the dual of my triadic Mobius matroid. If you want to know about triadic Mobius matroids or triangular Mobius matroids, then ask Dylan and Jeff, because they love those structures. They are best friends with those structures. So in this case, I may have to do all of these deletions. If I can't do a quick win, and I can't do any of the wins that I've described so far, then in this structure I'll have to do all of those deletions and 1 contraction, because I have an odd number of spokes, so I'm going to have to expose I'll expose 2 degree 2 vertices, but they're not really degree 2, they're incident with my hyper edge, and then I'll have to do a contraction in order to regain internal 4 connectivity. So what I will be left with is a triangular Mobius matroid. Which looks, a triangular Mobius matroid, you get it from, let me show you on this. So the hyper edge is kind of like a vertex. It's kind of indicating that there's a vertex that's incident with a bunch of edges. And when you do a contraction there, what you get is 2 vertices of high degree. And those vertices of high degree become hubs of your double wheel. This is not exactly what you get. What you get is obtained from your double Mobius wheel by removing this edge and adding a hyperedge that's incident with these 4 vertices. So this is your triangular Mobius matroid that you get as your minor. And this is internally 4 connected. Because even though that looks like a degree 3 vertex, it's incident with a hyperedge, so it's okay. And the last option that you can have in our theorem is you can be an interesting pair. So in all of our in our first 7 papers, we deal with matroids that are 16 or more elements. And it's just a really convenient bound. And if you want to look at binary matroids that are up to 15 elements, that have to, and we want to find an intermediate matroid between that matroid and our minor, then we just say, Dylan, you're pretty good with computers, why don't you find out what every single pair of matroids that we may have missed, that are small. And then we'll say, just put that up as a new paper, and we'll just reference that, and that's pretty easy for us. Thanks, Dylan. You're the best.
He's a real sage, isn't
Yeah.
Yeah.
Well, I think the definition's changed there. Can't remember what it. Shouldn't there be some reference to the fact that?
Are you talking about fascinating pairs?
I don't know.
So in your paper, there's fascinating pairs and there's interesting pairs, and every fascinating pair is an interesting pair, but not every interesting pair is a fascinating pair.
What's a fascinating pair again?
A fascinating. I'm going to refer you to Dylan Mayhew, who's an expert on that subject.
Okay. Yeah. I'll have to download the paper sometime.
Oh, it's really good. It's really good.
Yeah.
It's got a lot of code in it. It's really fun to read. So an interesting pair is a noun. You have at most 15 elements in M, and you have N as an internally 4 connected minor of it, and there's no intermediate matroid that's internally 4 connected. That makes it an interesting pair. Interesting pair means we haven't dealt with it yet, and we have to, because if there's not a quick win, then maybe it may be the case that our moves don't cover it. So there's 31 interesting pairs, and you can read all about them in an archive paper called A Splitter Theorem for Internally Four-Connected Binary Matroids, small matroids. So if we take parts 4 and 5 and stick them into the statement of the theorem in a slightly different way, then we find that then you're able to fit the whole theorem onto one slide, which is a nice thing to do. So here's the statement of the theorem in all its glory. You have M and N internally four-connected binary matroids, where N is a proper minor of N. Then there exists an intermediate matroid that's internally four-connected. That's at most 3 moves away from N, so it's quickly. Or you have that M and N are Mobius ladders or Mobius matroids, or they comprise an interesting pair, or up to duality, M prime is obtained from one of these moves, where the dashed edges are deletions and the arrows indicate contractions. So that's pretty exciting. So compare and contrast. The splitter theorem that Johnson and Thomas did, they require that H has a certain structure. Basically, if you have H being like a cubic ladder, then you don't have a bigger quartic ladder as a minor in H. I mean in G. They have one unbounded move from H to get an internally four-connected intermediate graph. They have 4 nice bounded moves, and by bounded I mean size almost 4. To move from H to get into an intermediate graph, but it might not be internally four-connected. And particularly in the M contraction, that's not necessarily going to be internally four-connected. And it's useful for finding excluded minor results. In their paper, they showed that it's really easy to use the result to get the result that every graph is planar, or it's K5, or it has K33 as a minor. And they did another thing with an 8 vertex cubic ladder. What happens when you try to exclude that from graphs? And they showed that using that theorem is really helpful. And in their paper, I should mention, in their paper they say that they're working on another paper that's going to clarify some of these results and develop more results, but that paper never came out. So I don't think that this is what they intended to leave. I don't think this was the final form that they had in mind, but that's what's in the literature. On the other hand, the Chun-Mayhew-Oxley splitter theorem, it gives no restriction for N. We have several highly structured unbounded moves from M, this should be an M, from M to an internally four-connected intermediate matroid. And we have some nice bounded moves. So it's either highly structured or it's bounded. And that's a matroid. Goodness, there's a couple of typos on the sides. And it's going to be useful for finding excluded minor results along the same vein as the Johnson-Thomas result. So this is our theorem, and you get, as a corollary, a theorem for graphs. And here, as I said before, the ladder structures can't have 5 co-circuits, so I actually am sure about those 4 co-circuits. In the previous slide, it was ambiguous as to whether it was 5 co-circuit or 4 co-circuit there. But in the graph case, you're going to have 4 co-circuits. And in the graph case, every 4-element co-circuit is vertical. They need a vertex. So this is slightly different from the preceding result in that we're not allowed to have Mobius matroids. Those are not graphic structures, so that's thrown out of our possible results. So if I have 2 internally four-connected graphs, then there's an intermediate graph that's going to be a quick win, or I've got a pair of Mobius ladders, or I've got an interesting pair, and now we drop down to 12 interesting pairs from 31. Or I'm going to do one of these moves, and the moves are all the same except that the structures are a little bit more highly structured. You have less ambiguity. And if you were to up the bound on your quick win from 3 to 6, then you can throw away all of your interesting pairs, because those interesting pairs don't arise then. The gap between N and M in your interesting pairs is going to be at most 6. So your theorem becomes even shorter. So either you're going to have Mobius ladders or Mobius matroids, or up to duality, you have to do one of these moves. And that's it. That's the easiest, cleanest statement, just putting it up to 6. Thank you very much.
Questions?
How many chapters are you up to?
7 is about ready to be submitted, and 8 will be the final one.
I just said, wow.
I asked this to James last time. Do you have any corollaries or applications?
So no, we're still in the process of writing things down and then writing more things down and then writing more things down. It seems like the case analysis, and there may be a better way to do it than the way that we're doing, but the way in which we're doing, it's extremely tedious and bafflingly complex. So the write-up has taken a lot longer than all the conceptual work, which we finished really like maybe a year ago. Finished all the conceptual work, and now it's just the write-up. And once we have everything written up and submitted, then we are going to think about a lot of applications. We're going to think about all of the applications at that point.
Isn't Guali working on applications?
That's a question about that. Yes.
Yeah, no, Guali Ding is interested in applications of the splitter theorem. Graph theorists are interested in this. Currently, the splitter theorem that you have for internally connected graphs, it doesn't guarantee the connectivity of your intermediate graphs. So.
Do you know what Guali is working on? What classes he's trying to characterize?
Just lots and lots and lots of
He's into
Tons of
kind of
them. All of them.
excluded. He's like, if we exclude this, then what are the graphs that are mean? He's kind of into those kinds of questions.
And he uses the Johnson and Thomas result over and over again.
Yeah.
But it's a real obstruction to him that you're not necessarily internally full connected. You've got that move.
So, can I ask a question that's sort of a practical question? So you got these pictures, and so there's some sort of generic representation of binary matrix using graphs in some sense. Can you do that? I mean, do you do that all the time in practice when you're doing it?
Yeah. Mm-hmm.
And can you do it? Is there always some sort of canonical thing that you could have when you just like geometric representations aren't particularly good, but they're more than useful when you're thinking about structures. Can you do this in some working in binary matrix? You can sort of think about graph structures, but then you embellish them in some way to represent co-circuits and things like that.
Well, they're matrices actually. I mean, what you're doing is the vertices of the rows and the edges of the columns and the hyper edges along the columns.
Okay.
So they, they're really, it's a graph or a representation of a binary matrix. It's the same thing. So it's,
As soon as we eliminated dealing with quads, so I keep saying quads, and I should tell you what a quad is. A quad is a 4-element set that is a co-circuit and a circuit, and
Isn't that DAG in literature?
DAG, maybe.
Isn't that in what there's in the literature? Am I wrong?
moving right along.
So those structures, I mean, you can draw a 4 co-circuit circuit that is graphic, but once we eliminated that, it was much easier to draw these objects in a standard canonical.
No, I was just curious about that.
Yeah. I mean, they were extremely helpful because these are the structures that give you problems. As soon as you remove an edge, you say, well, if I remove this edge and I kept my minor, then I'm all good unless I've created a big separation, in which case maybe I can deal with it. Or I've exposed a 4-fan, and 4-fans are just, it's just easy to. Although when you just have a 4-fan, there's you can change around the order that you
I mean, it is interesting, isn't
What do
it,
you think
that
about
the
the
problematic
elements?
structures turn out to be very close to being graphite.
Graphite.
Yeah,
Yeah.
they're, yeah, it's really
That
just
shows how
graph bubbles.
degenerate graphs are.
Yeah.
Alright, thanks Carolyn.